I welcome you all in the next lecture of quantum mechanics. So in previous lecture, we have already seen how the position and linear momentum operator does not commute. So that's why we have proven that the position and momentum operator like x and p that was not equals to 0. If I am talking about x and p, that means xt of psi minus px of psi that will not be equals to 0. And we got x p of psi that was equals to minus of ih. And here we have also, it's very important concept when we talk about any particular thing in the quantum mechanics. Why? Because if two operators are not commuting with each other, then that means they does not share or they do not share the the eigenfunction. And it's very important, the absence of common eigenfunction leads to the operator. That means that you cannot calculate the property like the position of the particle as well as the momentum of the particle, let's say p naught, simultaneously from the same wave function. That is the major limitations of this thing. And that's why that can be calculated as like delta x into delta t, that is greater than equals to h upon 2 pi. And this comes from the Heisenberg uncertainty principle that I am not going to discuss here, right? So this is what uncertainty is. Why this uncertainty is coming? Because of this operators are not commuting with each other. So today we will see that whether the momentum and kinetic energy or kinetic energy and the position operators are commuting with each other or not. So first I will try to tell you about how the kinetic energy operators looks, and then we'll try to derive this particular the commutation rules. So when we talk about the momentum operator, so we have observed momentum operator in quantum mechanics is minus I by h del by del x. And if I talk about the kinetic energy can be written as in case of classical mechanics we write kinetic energy is equal to p square by 2m, where p is the linear momentum. P is the linear momentum. So similarly here we can also write the kinetic energy operator is defined as T cap, and that will be equals to your T cap whole square divided by 2m. And let's try to substitute these things here. So if you substitute these things, that will be equals to del by del x whole square divided by 2m, and you will get this value as minus h square divided by 2m del 2 by del x square. So finally we are able to derive the kinetic energy operator, that is C bar, that is equals to minus h square divided by 2m del 2 by del x square. So sometimes it can be also written as minus h square divided by 2m del by del t. Is that clear? So you don't have to get confused because this can be written as in both these ways. Now coming to the very important concept to check whether the kinetic energy operator and the linear momentum operators are commuting with each other or not. And in order to check that thing, so we can write that let's say P cap is your linear momentum operator and T cap is the kinetic energy operator, and I will operate over that side. So that can be written as P cap psi minus T cap psi. It's very important concept. So let's try to assume this equation is our equation 1. And now I'll try to expand first this part. So if I expand this T cap psi, that will be equal to, I'll write T cap as it is, and that will go like T cap psi. And finally this can be written as your T cap. And what is T cap? T cap we have already derived, that is equals to minus h square divided by 2m and del 2 by del x square psi. And this can be written as your T cap, and that will be equals to minus h square divided by 2m del 2 psi by del x square. And once now this particular function you got, and this functions will get operated by this P operator, and finally you can say that minus IH del by del x minus h square divided by 2m del 2 psi by del x square. It's as simple as that. And finally, if you calculate this particular value, if we calculate this value, so what we will get? So the value of t cap psi you will be getting from here, there, that is equals to I h cube divided by 2m and then your del q psi by del x cube. So let's say this one is my equation second, right? So till now we have derived this part of this equation first. Now I'll be deriving the second part, that t cap psi from the equation first. So let's try to derive these things. T cap psi. So t cap I will keep it as it is, then it will get operated like t cap psi, and then I can write that t cap, okay, and then t cap is like minus I h del by del x of psi, and finally you can write these things like t cap. So now this t cap you have to operate over that function that you got there, that is equal to t cap is what? Minus h square divided by 2m, okay, and then h cap. So del 2 by del x square minus I x del by del psi by del x. So if you operate these things, then you will be getting I h cube divided by 2m and del 3 psi by del x cube. So the value of t cap psi, you are getting this one. So if I am assuming this one is my equation 3, so from equation second and equation third, what you can see, if I rub these things here, so you will be getting the value of p cap psi minus p cap psi, that will be equals to what? So I x cube divided by 2m del 2 psi by del x cube minus I x cube divided by 2m del 2 psi by del x cube. So if you see this both terms are equal, so finally you will see here that p cap psi minus p cap psi, that will be equals to 0. That means you can directly write these things as p cap minus p cap psi. Sorry, this will be written like that. So finally you can see the linear momentum operator and the kinetic momentum, kinetic energy operator commutation is 0. So here you can see that this particular result clearly tells you that the kinetic energy and the linear momentum operators are commutating with each other. The reason is, and what is the physical interpretation of that thing? So let's say if you have a wave function and due to this commutation, what will happen? There will be some common, the eigenfunction for both of these, and then you can clearly calculate the, you can directly calculate the linear momentum and kinetic energy of a particular wave function or particular observable from the same eigenfunction, and that is the physical significance of commutation of the kinetic energy and the linear momentum operator. Okay, thank you.